We're continuing our study of polynomial functions with looking at their graphs. So we've already talked about how a polynomial function is defined as something that looks like this. Where you've got a degree and a leading coefficient. And smooth and continuous. If it's smooth, then there are no corners or cusps. And if it's continuous, then there are no breaks or holes. So smooth and continuous would look like that. Okay, the end behavior of a function is talking about how is the function behaving as it approaches negative infinity and infinity. For one thing, if the leading coefficient is positive, then as we go to positive infinity, we're going to move up to the right. As we go to negative infinity, if the leading coefficient is negative, it would go down to the right. And we'll look at some pictures of that further in a minute. The leading coefficient test says as x increases or decreases, the graph of the function eventually rises or falls. So that leading coefficient reveals its end behavior. So here's the pictures. So for the first picture, if the leading coefficient is positive and n is odd, so your highest degree, your degree of your polynomial is odd, like 1, 3, 5, or so forth, and your leading coefficient is positive. So for example, 3x cubed plus 2. Of course, that's not that graph, but that's an example. So that's saying that your leading coefficient is positive and your n is odd. Then it's going to fall to the left and rise to the right. So what we say is as x approaches negative infinity, f of x approaches negative infinity. See, as we go to the right, we're going down. That's what that's saying. As x approaches positive infinity, so as we go to the right, it's going up. So f of x approaches positive infinity. If n is odd, so we can have f g of x equals x cubed again. It's not letting me write down there. Let me do it. But it says that a is less than 0. So a negative leading coefficient. Then it's going to rise to the left and fall to the right. And that is incorrect here. So I'll fix that on your paper. So don't look at that. It should be, we'll go ahead and change it. It rises to the left and falls to the right. Like I said, I'll fix that in your notes. Okay, so we would say as x approaches negative infinity, then f of x goes up, so it's approaching infinity. And as x approaches infinity, as we go to the right, we're falling, so f of x approaches negative infinity. Then if n is even and the leading coefficient is positive, then we're rising to the left and the right. So it's going up, up. So like this one would be, say, 3x to the 6th plus 1, something like that. Even n and a positive leading coefficient. So we will say as x goes to the left, f of x goes up, and as x goes to the right, f of x goes up. And then the last picture, also where n is even, but the leading coefficient is negative. So like negative 2x to the 6th plus 1. So it falls to the left and right. So as x approaches negative infinity, f of x approaches negative infinity. As we go to the left, we fall. And as we go to the right, as x approaches infinity, we also fall. F of x approaches negative infinity. So for example 1, we want to use the leading coefficient test to determine the end behavior of this graph. We've got f of x equals x to the 4th minus 4x squared. So our degree, or n, is 4, which is even. So even means either we're going to go up, up, or down, down. Our leading coefficient is 1, which is positive. So positive leading coefficient means we have to rise to the right. So we're either going to go up, up, or down, up. So which one is for both? Up, up. So we'll say as x approaches negative infinity, f of x goes up. It approaches positive infinity. And as x goes to the right, approaches positive infinity, f of x goes up to positive infinity. And there's a picture of it. So you can see up, up. Then let's look at part B. So for this one, you don't necessarily have to multiply this all the way out. Basically, just look at the fact that we've got a 3 on this x and a 1 on this x. So that means that your degree will be 4. And your leading coefficient will be negative 2. So since we are an even degree, it's either going to go up, up, or down, down. And the leading coefficient is negative, so it has to go down to the right. So that means we're down, down. And we write that as x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x approaches negative infinity. I know that one wasn't in your notes, but that's okay. It's good to look at. And there it is. Oh. No, it's not. I've got a plus in there, so forget that. It should look something like that. Okay, so zeros of polynomial functions. You can find the zeros of a polynomial function by factoring it, just like we did with quadratics, and setting each factor equal to 0. So for example 2, find all the zeros of this function. Now, later on in future sections, we're going to look at how to do this if it doesn't factor. This one, fortunately, does factor easily enough. So we can factor this one by grouping. We can take an x squared out of that first group and be left with x plus 2. And we can take a 4 out of the second group and be left with x plus 2. So this factors to be x squared minus 4 times x plus 2. And we could factor it even more to be x plus 2, x minus 2, and then x plus 2. But we don't have to do that because we're just trying to find the zeros. It didn't ask us about factoring. So we just need to take each of these and set them equal to 0. So x squared minus 4 equals 0, and x plus 2 equals 0. So x squared is 4, or x is plus or minus 2, and x is negative 2. So the zeros are at negative 2 and 2. And here's the picture. You can see that we have a 0 at negative 2 and at 2. The next thing we're going to talk about is multiplicity. And what has happened here is we found that there were 2 instances where negative 2 was a 0. And so that means that the multiplicity is even, or it's even multiplicity, so that's why it touched here. With positive 2, there was only one 0 at positive 2, so that means it crosses. It's an odd multiplicity. And that's what this says here. So looking at an example, it says find the zeros of this function and give the multiplicities of each 0. So first we're going to look at, we don't really have to mess with the negative 4. So we'll look here. X plus 1/2 equals 0. So x is negative 1/2. This has an even multiplicity because the degree is even. And if it has an even multiplicity, that means that our graph touches at x equals negative 2. And then for this one, x minus 5 equals 0. That's x equals 5. The degree is odd, so it has an odd multiplicity, which means that the graph crosses. So you can see here at 5, it's crossing, and at negative 1/2, it's just touching. The intermediate value theorem says a bunch of stuff here, but let's look at a picture. It says that if you've got a graph, say something like this, and you have A and B, like this. And when you plug in A and B, this is f of A and f of B, actually, and they are different signs, so one is positive and one is negative, then you have a 0. That's all that's saying, okay? A bunch of words there, but if you plug in one number and it's positive and another number and it's negative, then that means that there is a 0 between those 2 points. So, for example 4, show that this polynomial function has a real 0 between negative 3 and negative 2. So plug in negative 3 and plug in negative 2. F of negative 3 is negative 42. And f of negative 2 is 5. So since the degrees are opposites, one is negative and one is positive, or we can say that there is a sign change, then that means that there is a 0 between negative 3 and between negative 2 and negative 3. We don't know what it is, but we know that one exists. And there it is. Turning points. If a function has degree n, then it has at most n minus 1 turning points. So if your degree is 5, then it has at most 4 turning points. If your degree is 8, it has at most 7 turning points. Here, the degree is 3. So you have at most 2 turning points. It could have less, but you can't have more. So here's a turning point, and here's a turning point. A strategy for graphing polynomial functions, you can read through this. We will be graphing them, and I'll go through an example, so I'm not going to read through this, but you can use this as a guide when you're graphing polynomial functions. Yes, there are several steps. For example 6, it just wants us to tell which one could be a polynomial function. For those that could, list the real zeros, state the least degree the polynomial function could have, and for those that aren't, say why not. So for this one, it has a corner. So we are not a polynomial function. Because of the corner. Part B has no corners or cusps, and it is continuous, so it is a polynomial function. And we were asked to state the least degree and the real zeros. So the zeros, where it crosses the x-axis, so they are at -2, 0, and 2. And then it wants to know what would the least degree be. So we look at our turning points. There are 2 turning points. So that tells us that n minus 1 is 2. So n could be at least 3. So if there's two turning points, there's one more for the least degree. So the least degree would be 3. And for this one, it's not a polynomial because of the break. Then example 7 asks us which of these functions could be the graph of x to the 5th plus ax to the 3rd plus bx squared minus 2x plus 3. So we're looking at several things here. Let's first start with the end behavior. So since we have a degree of 5 and a leading coefficient of 1, so we have an odd degree and a positive leading coefficient. So that means that we are going to be even going up to the right because it's a positive degree. Or, okay, we're going to be going down up or up down because it's a odd degree. And since it's a leading coefficient that's positive, we're going to be going up to the right. So we're going down, up. So it cannot be D. Okay, what else do we look at? We can look at the 0, or rather the y-intercept, because we could easily find the y-intercept here. I know we've got this a and b in there, but that's okay, because if we plug in f of 0, it's going to get rid of a and b. So we'd have 0 to the 5th plus a times 0 to the 3rd plus b times 0 squared minus 2 times 0 plus 3. So you're getting rid of everything but the 3. So it has a y-intercept of 3. So that means it can't be B, it could be A, and it could be C. What else? What about turning points? So the degree is 5. That means we have a maximum of 4 turning points. So let's see. B has 1, 2, 3, 4. So B would work. C has 1, 2, 3, 4, 5, 6, 7, 8. Nope. C's not going to work. The only graph that would work would be B. Okay, so let's graph 2 of these and then we'll finish up the section. So use our 5-step strategy to graph f of x equals 2 times x plus 2 squared times x minus 3. So the first thing that we need to look at is the end behavior. So we have a leading coefficient that is 2, and that is positive. Our degree will be 2 plus 1, so 3, which is odd. So that tells us that we have the situation where we've got a positive leading coefficient and an odd degree, so that is down, up. So we say, as x approaches negative infinity, f of x approaches negative infinity, and as x approaches infinity, f of x approaches infinity. So what I like to do is over on my graph, I'm going to make a down arrow here and an up arrow there so I know what's happening so far with my graph. Next, turning points. So the degree is 3. So that means we have at most 1 less, or 2, turning points. I can't really mark that on my graph, so we'll just stick with that. Intercepts. We need to solve each piece for 0. So we've got x plus 2 equals 0, and x minus 3 equals 0. I'll write that different. So x will be negative 2, or x will be 3. So we have intercepts at negative 2 and 3. The next question is, are they crossing or touching? So for negative 2, we have an even degree, so that means we are touching. For x minus 3, there is an odd degree. So that means that we cross. Now, how I mark that on my graph is, if we're touching, we're either looking like this or this. It has to be the first one because we're going down, according to my pink arrow there. And then if we're crossing, it either looks like this or this. It has to be the first one because of the up arrow there. Okay. The next thing that we can find is the y-intercept. So we'll just plug in 0 for x. That gives us 2 times 2 squared times negative 3, or negative 24. So we cross the y-axis at negative 24, right there. Now we can pretty efficiently graph our function. So we know it's coming from down below and going up to -2 and just touching, and coming back down to go through -24. Then we know it's coming back up somewhere. So it's turning again and crossing over 3. So that is not, of course, the exact picture, but it's pretty close. We know it's touched and crossed. There's a maximum of 2 turning points. We know where the zeros and the y-intercept are, and we know that it's going down up. So looking at the actual picture, it's on your notes. I didn't include it on here, unfortunately, but it looks pretty dang close. And example 9, let's do this one more time. So end behavior here, we've got a even degree and a positive leading coefficient because it's 1. So that means that we are up. So as x approaches -infinity, f of x approaches infinity, and as x approaches infinity, f of x approaches, those should be arrows, infinity. So at the picture, I'm going to draw up. Turns, the degree is 4, so that means there's a maximum of 3 turning points. Our intercepts. Well, to find the intercepts, we're going to have to factor this. So I'm going to go over here. We've got and we can factor out an x squared. And then we'll set both of those equal to 0. So square root of 0 is just 0. And add 4 to both sides. Take the square root. We have plus or minus 2. So our intercepts are at x equals 0, x equals -2, and x equals +2. Then do they cross or touch? Well, looking back over here where we factored, 0 has an even degree, so it touches. For -2 and 2, the degree is 1. It's odd. So they both cross. So let's go mark that on the graph. Let's start with the -2 and 2. We'd have to go that way, because if we go this way, then we'd be going down to the left, and that's not going to work. And then to go up to the right, it's going to have to go that way across. Okay, so which way would we touch? Well, if we touch up here, then it's going to have to cross again. And that's not going to work because we didn't have zeros that crossed again. So it's going to have to touch coming from below so we can connect like this. And then last, let's find the y-intercept. It's just 0. So it only crosses the y-axis at 0. Okay, so let's graph it. We know we're coming from above and going down and coming up and just touching at 0. And we've got to go down and come back and cross. And it's probably pretty symmetric since we're crossing at -2 and 2, which are symmetric across the y-axis. And so it should look something like that. Okay, and that concludes our section on graphing polynomial functions. We'll look more at graphing and finding zeros as we move forward.